Bem-vindos à primeira Open Tech Week da Blip. Welcome to Blip's first Open Tech Week. As part of a multinational, multi-location group like Flutter, a lot of our work is in English, so that's how we will continue this event today. At Blip, we believe that the more we share, the more we learn and grow. This Open Tech Week is an opportunity to give back to the tech community, sharing our challenges and best practices, and creating an open space for learning with each other. We've talked about sharing technology that works across our divisions and brands. We've shared how we approached building a new betting experience for Betfair with quality embedded right from the start. And we discussed hosting and automation and some of the unique challenges we have to operate our platforms globally. You can play back all our previous sessions here in our LinkedIn event and reach out to us or our speakers directly. Today, we'll share more about the challenges we have had to help our brands manage the prices and risk on their websites. Each of our speakers will be able to answer any questions from you on the comment section of this stream. So please leave your questions and comments, and they'll be commenting back right after their talk. We'll start by hearing from António Pires, backend developer on our risk and trading department. As a backend developer on risk and trading, António builds tools to help the company manage the risk of its daily activity and keep traders informed on the trading floor. In his talk, Place Your Bets in gRPC, he'll talk about how his team transformed their bet ingestion system. Welcome, António.
Hello, thank you, Mariana, for the introduction. And hello to everyone. Thank you for joining us today. My name is António, and I'm a backend software developer at Blip. I work at the risk and trading department, and today I would like to show you one of the components my team is responsible for, and tell you about the challenges we are having maintaining it, the main problems we needed to solve, and how we redesigned the system and the improvements we got using gRPC. But before going into details, I would like to introduce you to the problem the system was solving. And as Mariana said during the introduction, in my team, we work with tools that help the company manage the risk of its daily activity. And one important capability that we need to have so that our risk management tools can work properly and present relevant and reliable information to our internal users is the ability to ingest large quantities of betting information and make it available to and usable for other components downstream. And doing this is the job of the system that I'm going to show you, our bet ingestion system. First, let's understand where are bets coming from, because bets are the inputs of our system. I don't know if you have ever done a bet, but our customers can go, for example, to our Betfair mobile web app or Betfair website, browse the list of games, and if they see something interesting, they can place a bet with some stake. In this case, in the example that we have here, the user placed £100 for Benfica to win next match against Porto. And in my opinion, I think that it's not the best bet. I'm not an expert, but I think that's these kind of bets where people lose money. But the bet was placed, and there is nothing we can do now. The bet is already going through our system, and we will receive it in our bet ingestion service through the Betfair bet source. This diagram shows a simplified version of how the system looked like before our changes. This specific bet came from the Betfair website, but we don't receive bets only from Betfair. We receive them from multiple bet sources from different brands all over the world, and some of them from within the company, but we also receive data from other partners. Basically, every time someone places a bet in one of these websites or physical stores, we receive it here. After we receive the bet, you can see that it goes through some different services and queues, and finally ends up in a Rabbit cluster. And from there, it is consumed by multiple risk management services that use that information to do their risk management jobs. Actually, if you watch the next session with José Brandão, he's going to talk a bit about one of them. But this can seem a complex system, and for sure, it is handling a lot of data. But in reality, it is solving a relatively simple and common problem. But the way it is solving this problem was making our job of maintaining it very difficult. Let's go through the reasons why. What were our main problems with this? First, we have these multiple sources sending data into the system, but you can see that there are as many multiple different ways for our partners to integrate with us. We have data coming in via Rabbit, Azure queues, REST APIs, and it is not always easy to manage all of these different integration points. Another problem was that a lot of those sources were sending messages in their own format, which required us to make transformations on them so that we could aggregate everything in a single stream in one coherent model. But the problem was not only the model itself, but because we were using JSON format, even sources that were following an agreed format could be sending different values inside some properties. For example, you can see that here we are receiving bets whose bet type field have an S, an SGL, singles with an S in the end, and they were coming from different sources, and in the end, all wanted to say the same thing, that the bet that has been placed was a single bet. And if we wanted to keep coherence, we had to do the adaptation work ourselves, or else our consumers would receive these and would need to do the work on their side, which they should not do, or at least they shouldn't need to do. To deal with these transformations and other validations for some of the sources, we have more boxes in the middle of the flow. These are all separate microservices, different code bases, and now imagine we need to do some model change, add more information or update some field. Doing things like that involves a lot of overhead. We needed to touch multiple services, and some of them were very legacy. The team was not that comfortable working with them. They were deployed in old infrastructure with pipelines that were not always working as expected. And besides that, we needed to be careful not to break any compatibility between them. The way the system was designed made it very difficult to grow and change. There was no defined process to integrate new sources. And when we needed to do it, it was hard work, very time consuming, not only for our team, but also for the partner developer teams that were trying to send their data to our site. And all of that data was flowing not through one, but multiple Rabbit clusters, and they were already reaching their limit capacity. And this was not the biggest problem. The bigger problem was the system was basically coupled to Rabbit. You can see that the boundary of our system is traced after the Rabbit cluster. And if we wanted to move away from it into another solution, for example, a Kafka, we needed to change a lot of other services. And that involved a great amount of work and uncertainty that we couldn't run away from. And this solution worked. It did its job for a long time. But the existing sources were sending more and more bets every day. And with the mergers and acquisitions the company went through in the past years, the load the system needed to handle increased a lot to levels that the system was not designed for in the first place. And besides that, we were expecting to integrate new sources soon, which would increase again the pressure on the system. And all of this made us realize that we really needed to change something to make our lives easier and the service more robust. We started asking ourselves, what did we want? And the problem was not only technical between the actual services that were trying to exchange data between them. but also the communication between the development teams on each side was being on each side of the communication. We needed a different way to handle that communication between the teams. We wanted to create a coherent API, a single entry point for all that information, a way to enforce a single model for all sources, give partners an easy way to onboard, giving them responsibility of sending us data in an agreed format, a format that needed to be easy to share, and at the same time, not limiting the way they could do their integration, giving them the possibility to work with whatever platform or language they feel more comfortable with. We also wanted to be able to ensure compatibility and not break partner integrations as the product evolved. We wanted to be able to make changes, if possible, with no dependency on other teams, be completely asynchronous. We did not want to be maintaining logic to support multiple API versions, so old clients would break and then wait to be sure everyone was now migrated to new version before being able to get rid of the code. We wanted to try to remove these kind of limitations. It was also very important for us to be able to scale our infrastructure when required. If the load increased, we wanted to easily scale according to the needs. For example, when we have Champions League matches or Cheltenham races or during Grand National, we receive an unusual amount of bets and we need to be ready to handle them. And finally, we wanted to move away from Rabbit, probably into a Kafka solution, a transition that was already taking place company-wide. But at the same time, we did not want to make the same mistakes and end up locked with Kafka this time. We wanted to be able to easily change the technology we use for streaming our data, and if we need it in the future, it should be easy to do. And that's when we started looking into options, and at gRPC in particular as a possible solution for a lot of these problems. And we found that gRPC, protocol buffers, and a small service running in Kubernetes could be just enough to fit our needs. Well, gRPC. gRPC is an efficient remote procedure call framework. It was born from an internal Google project called Stubby, and gRPC is kind of a rewrite open source version of this project. And everything, every single piece of it was designed with simplicity and efficiency in mind and optimized for performance. And why did we choose gRPC? First, it is not platform dependent. It works everywhere, Linux, macOS, Windows, and is also language agnostic, which were two major points for us because we did not want to be imposing these restrictions to any partner. You can have different teams working on different languages, a C++ server and a Ruby or a Java client, and it is not a problem. All they need to agree on is the service definition and they can talk to each other. It was also designed to automatically generate idiomatic client and server stubs, providing a standard structure for developers to use, which greatly reduced programming effort, saving a lot of time. gRPC hides all protocol, transport, and mapping details behind a simple, clean interface that we can just extend with our business logic, and which does not happen in the usual REST or OpenAPI approaches, where these details are exposed to the user. And defining the way services talk to each other involves a lot more design decisions and communication between teams, which can be tricky sometimes. gRPC makes the integration distribution of the API contract incredibly simpler. With gRPC, we can do more than the typical request response flow. It natively supports streaming. The client can do streaming and the server can do streaming, and they can both do streaming. We can have bidirectional type of connection that is like having your own TCP, but based on application messages. And although if you use this, you will need to handle a bit more complexity. It's great for some use cases. Besides these advantages, there are all that are already amazing. It is highly performant and widely tested. It is used in production by several large companies and projects like Netflix, Cisco, or Spotify. And I think that you can see a couple more of them in gRPC.io website if you want. It is highly extensible and customizable. There are plenty of extension points where you can do your own integration or use some of the ones already available on the community. It supports different solutions for health checking, transport, load balancing, tracing, authentication, a lot of stuff. And gRPC uses HTTP2 as its default transport, but the gRPC core is basically a thin layer on top of some transport, we just saw, the transport is customizable, and you can use other implementations like Quick or Coronet. But HTTP2 brings its own advantages, provides a foundation for long-lived real-time communication streams, and brings a lot of benefits like compression, lighter network footprint, bidirectional streaming. And then gRPC builds on top of that foundation with a lot of other nice features like connection pooling, else semantics, efficient use of data frames, error cancellation, and deadline propagation, which can be really helpful when you have big network of RPCs. And all of these capabilities that gRPC give us for remote calls are all great and useful. But to communicate between services, we still need to use some kind of encoding so our objects can travel through the network. And gRPC is also agnostic when it comes to encoding. It allows us to use any encoding we want. We can use XML, JSON, or even create our custom way to encode our data objects into a single string. But by default, gRPC uses protocol buffers, or simply protobuf as its interface definition language and data serialization protocol. They work great together. There is a nice mixing of the two projects, and protobuf brings a lot of other advantages to this mix. You can imagine protobuf as JSON or an XML, but a lot smaller and faster. Messages are serialized into a binary data representation, which is a lot more compact, and this greatly reduces network load. Serialization and deserialization times are a lot smaller, which results in a better overall performance. And besides these performance improvements, using proto format for both data and service specifications simplifies a lot the definition of service contracts. You just need to write a proto description of the data structures you want and put your schema and API under version control, and the communication between development teams, it's much easier. Then you can use this definition file to generate a class that provides getters and setters for each field and avoids the need to write marshalling and marshalling logic. There are code generators for basically all your favorite languages, so there is no reason for you not to use it. It is strongly typed. Clients receive typed objects rather than free-form JSON, and because of this, they can reap the benefits of auto-completion in their IDEs and type safety if their languages supports it. And with this feature, we can, for example, define an enumeration type, which would help us with the problem we had with the type property, the bad type property that I showed you in the beginning. Another important factor in favor of protocol buffer format is that it was heavily intended to be backwards compatible. It supports the idea of extending the models over time in a way that we can still read data encoded with an old format. This was really important for us. So the server API could be updated to a newer version and clients could still send their old format and nothing would break. Basically, summing up, with gRPC and protobuf, we end up with a lean platform using a fast transport system that needs to deliver smaller payloads, resulting in an overall decrease in latency and size of our remote procedure calls. And not only that, but we get the ability to distribute our API updates quickly with code generation and asynchronously with backwards compatibility. This sounds amazing. Finally, I want to show you how does our service look like after the transformation. And this is it. We were able to transform our batch ingestion system into a highly scalable solution that can handle thousands of batches per second. We are not finished yet with the migration, but the initial performance tests are very promising. We are able to consume more than 40,000 batches per second. This with only 2 backing nodes, each one with 4 CPUs. And at the same time, it allowed for smoother inter-team communication and a faster integration of newer sources. Do you still remember how it looked before? This version looks a lot more convoluted, and I'm sure you would prefer to be working with the newer one. And remember, this is a simplified version. There are a lot more boxes and arrows in the real one. So let's go quickly through our initial list of things that we wanted and see if we could fulfill them all. First, we wanted a single point of entry for every batch source, and that's what we have now. A single API served by a single endpoint that clients can use to send their information. We have multiple instances of the service, and we use an AWS ALB load balancer that splits the traffic between them. We now have a contract that we can enforce, written in protobuf and under version control, a lot easier to share and completely agnostic for clients, which can use any language they want to implement it. This API is also easy to update without breaking older clients. We don't need to worry when we make changes or even to adapt what sources send. To avoid breaking downstream consumers, we can just release a new version of the API and inform our partners they can use it. This resulted in a drastic reduction in the latency to introduce new sources and extend the platform. A lot less work for our team and also easier for teams that want to integrate with us. The system is highly scalable and can ingest thousands of bytes per second when we need. We can easily adjust the number of backing nodes, and we are not going to be overloaded by bytes anymore. And finally, we moved away from Rabbit, not completely yet. As I said, we are still migrating sources, but we are getting there. The final goal is to send everything through Kafka for downstream consumption. And this gRPC entry point allowed us to easily handle client authentication. We can have a single authenticated entry point into the cluster instead of exposing the Kafka brokers to external producers. And more importantly, it removes our dependency in a specific messaging system. You can see that the boundary of our system moved back. And now if we want to change it, it is relatively easy to do so. And we only need to worry about a single code base and a single service. Microservices are becoming more and more widespread, and I think gRPC is a great solution to solve backend to backend communication. I think that sometimes still remains kind of crafty and cumbersome. So I recommend you to take a deeper look into this tool and try it, because you'll probably find that you can cash in on its benefits. And that's all from my side. Thank you for your time. I hope you could get you interested in exploring gRPC and curious about the challenges we have here at Blip. If you want to reach me, you can use one of those channels. And don't leave just yet. Watch the next talk that is going to be very interesting and about one of the consumers of this system.
Thank you, António. António will now be answering your questions in the comments section of this stream. And we'll now hear from José Brandão, also a backend developer from Risk and Trading. As a backend developer in Risk and Trading, José has been building several real-time applications that enable our traders to get relevant information as fast as possible. When dealing with streaming applications, we want low latency. A common use case is enriching real-time data. To do so efficiently, we keep our data access local, which can raise several challenges. In his talk, Stateful Stream Processing with Apache Flink, José will explain how Apache Flink can help such situations. Welcome, José.
Hello, everyone. Thank you for the introduction, Mariana. As mentioned, I'm José Brandão, and I'm a backend developer from a special department within Blip, which is Risk and Trading. In the last almost 4 years, I've been developing applications for traders, which are the ones responsible by managing the risk of a betting company. When dealing with real-time data, ensuring that we deliver it to traders as fast as possible is a constant concern for us. Today, I will speak about what is Apache Flink and why we use it, especially for stateful stream processing. A stream, as you all know, is an infinite source of data, which we typically want to consume in real time. So we are constantly listening to events. And by stateful stream processing, we understand that we'll need to remember past events that flow through our system. Before talking about any Flink specifics, let's quickly consider a practical use case of data enrichment. Imagine we have a stream of football bets where we receive a bet whenever a customer places one in any of our platforms. For instance, on Betfair, when a client bets £100 for Benfica to win a match against Porto. We want to enrich this stream of bets with another stream that provides information about football teams. Plus, we want to do this while adding minimum latency, meaning that our enrichment should be done as fast as possible. And we want the football team data to be up to date when we perform the enrichment. Looking at it with more detail, we receive a stream of football bets placed by our customers that's coming from an external system, let's say Kafka. Here we can picture a naive model of a football bet that has several properties, including some related with both home and away teams. Sadly, we only have the ID for each team, and we would like to enrich these home and away properties with many more fields. That's where our football team data stream comes in, and it can be as well a Kafka stream. And it will provide us a lot of information about the team, including its name and some stats for the current season as their scored goals and yellow cards. I can tell you that if we have to store this data for all the teams in the entire universe, it will be in the order of hundreds of gigabytes. And as you can see, this data is constantly changing because a team can score a goal at any time, and we want our bets to be enriched with the most up-to-date football team information. Essentially, we want our application to combine these streams and to produce an enriched bet stream. If you look closely on this last sample of a payload, you can see that these stats are totally random and that I have no bias for any of the teams. Now, let's recall our initial requirements. We want to enrich bets with football team information while adding minimal latency. In this moment, I would like you to picture how would you implement this. If you did this mental exercise, an immediate question probably is, how can we have the football team data up to date and ready to be queried? A short answer is we could build a state around it and persist it somewhere so that it can survive application restarts. This state also needs to allow fast queries in order to avoid adding considerable latency for reads and writes. So ideally, it would be somewhat local. Also, in our scenario, as António said in the previous talk, our business is constantly growing and our pet throughput is always increasing. Probably, we will need several instances of our application. So if we scale it to distribute the load between the different instances, I would like to share the state. Otherwise, we would be replicating hundreds of gigabytes per instance, which would result in a heavy storage footprint. Achieving such characteristics can be a bit complex, and that's where Apache Flink joins the conversation. So what is Apache Flink? It is an open source framework developed by the Apache Software Foundation that promises high throughput and low latency. It is used by several big companies like Apple, Netflix, and Reddit. It has capabilities from the range of stream to batch processing, and we can develop Flink applications in Java, which is the case of the team I'm on, but also in Scala, Python, and even SQL. Flink is also a distributed processing engine, meaning that applications are parallelized into possibly thousands of tasks that are distributed and concurrently executed inside a cluster. Therefore, an application can leverage unlimited CPU, memory, disk, and network I/O, what allows us to run applications at any scale. It requires computing resources in order to execute applications, so it integrates with cluster resource managers as Hadoop Yarn, Apache Mesos, and Kubernetes. And there is also the possibility for a standalone cluster deployment. Now, let's see what are the main features of Apache Flink that can help us with our problem. One feature of Flink is that it offers high-level APIs and low-level APIs, basically a trade-off between conciseness and expressiveness, and targets different use cases. So if we want fine-grained control over our applications, we have it. But if we want simplicity, we also have it. The data stream API, which was the middle layer, is what we need for our use case since it offers, as the name suggests, streaming capabilities. The flow is inherent to the streaming programming model, and it is how we define our execution graphs. We have sources, which are the entry points of our topology. Then we have operators in the middle that apply transformations to our stream. And we end up with sinks, which are our exit points or returning points. Sources and sinks are typically integration points with external systems, and there is already a good set of ready-to-use sink and sources that we can import into our applications. As we learn some things about Flink, let's see in general terms how we could implement our bet enricher. All our sinks and sources will be Kafka ones. We have our participant source at the top and our football bet source at the left, which are our entry points. Then at the right, we have our enriched bet sink, which is our exit point, and in the middle, we have some operators. Operators essentially allows us to transform one or more streams into new streams, and some examples are map, flat map, joins, and key by. And this last operator, the key by, is especially important because whenever we use it, we are partitioning our stream, well, by a given key. In fact, it transforms our stream into a keyed stream, which then allows our operators to use keyed state, which is a type of Flink managed state that gives us the ability to have the state partitioned by key in a key value fashion. I will explain what managed state is in a bit, but for now, let's see what other pieces of our enricher we can already add. We have seen that we have our participant source that will provide us a stream with data about all the football teams as Benfica and Porto, and we will key it by team ID. From this point, we are already dealing with a kid stream, which means that if we store any of this information, our state will be partitioned by team ID. Then, on the left side, we have our football bet stream, which is also keyed by bet ID. An example of a record is our Benfica versus Porto bet. And we know that each of our bets contains 2 participants, so we can split them to perform a parallel enrichment. At this point, we have our Benfica bet participant and Porto bet participant flowing as 2 different records in our stream. Since we are transforming bets into bet participants, and from each record we are generating 2 records, our splitter can be implemented with something that's probably familiar to you as a flat map. We have been speaking about state and kid state, so let's dive a bit into it. Application state is a first-class citizen in Flink since it offers managed state, which is essentially the capability to have state inside our Flink application, where Flink manages it and offers some nice features. Allowing stateful computations at in-memory speed, meaning that the state is always kept in memory, and if for some reason it needs to use disk, it will be extremely efficient. We can use, for instance, RocksDB, which is an efficient embedded on disk data store. It has an efficient checkpointing mechanism, which is the synchronous process where Flink periodically takes persistent snapshots of its state and copies these snapshots somewhere more durable, such as a distributed file system. We can use, for instance, S3 from AWS to ensure that our state files are safe. Due to this checkpointing mechanism together with recovery algorithms, Flink offers exactly one state consistency, ensuring the consistency of application state in case of a failure. It also claims to be able to manage large state in the order of terabytes, especially if incremental checkpoints are enabled, which is essentially using deltas, the difference between previous snapshot and current state, instead of full snapshot only. The state can keep up with scaling applications, meaning that if we need to scale our application, the state will be redistributed accordingly. Now that we have our bet split in bet participants, we can at this point key our stream by team ID. This allows us to cross information from both streams and enrich our bet participants with the respective football team data. The enricher can be implemented with some special operator which uses kid state to store our participant data, and that is also able to process bet participants using the state to enrich them. And most of this is abstract for us by Flink. We just need to deal with it in the context of a single record, so no concurrency concerns. The nice part is that if for some reason we decide that we want to have more instances of our enricher, our records are distributed across the multiple instances according to the keys. For instance, our Benfica bet participant could go to enricher 1, and that would mean that our Benfica team data would also go to enricher 1 because the key is the same in both cases. Due to managed state, our state will also be shared accordingly, meaning that enricher 1 will be able to locate the respective entry in the state for Benfica because it's now handling this key. At this point, we have all the problems we spoke in the beginning resolved. Our team data will be managed by Flink, so we can access it whenever we need. It will resist to application restarts. We can make queries to this state at in-memory speed, so no major latencies in state access. Our state is divided accordingly to the number of instances, so it also scales with the application. And Flink will be able to deal with our hundreds of gigabytes of state. To conclude our flow, when we finish our bet participant enrichment, we rekey our stream by bet ID again. We wait for both participants so that we can merge them into a bet. And finally, we produce the results and enrich bets into an outbound Kafka. Now, let's take a brief look on how things work under the hood. We have 2 main types of processes. The first one is the job manager, which is mainly responsible by coordinating the execution of Flink applications. It handles things like task scheduling, task failure, and coordinates checkpoints. Then our job manager interacts with another type of process, which is the task manager, that represents an actual worker in the cluster, meaning it is actually the process that executes the tasks that the job manager submits. And it is also important to know that each task manager runs on its own JVM. Task managers run in what we call task slots, and the number of slots actually determines the number of concurrent tasks a task manager can handle. This is configurable. We can determine how many slots we want per task manager based on the resources we have available. So a slot, it is actually a unit of scheduling. We have been talking about tasks, but I actually never told you what a task is in the Flink context. A task can simply be an operator, as for instance, our bet enricher, or a group of operators that Flink can make for us. For instance, we can decide to group our bet source and bet participant splitter into a single task because it will be more efficient. This is called operator chaining, and it increases throughput since there is less communication between tasks, so less overall serialization and deserialization, or even network. Whenever we increase the parallelism of a task, we end up with multiple instances, and those are called subtasks. For example, our bet enricher operator has parallelism of 3, which means that the task executing it will have 3 subtasks. The number of slots will actually determine the maximum parallelism we can define for our operators. With proper configuration, Flink will distribute our subtasks within the slots in a very efficient way. It ensures that subtasks of the same task will end up in different slots, and this is good because it results in optimization of our slots. For example, let's say our enricher is by far the heaviest task we have in our execution, and all the other ones are super fast. With the guarantee that we only have one instance of our enricher per slot, we ensure that no instances of enrichers will be blocking each other, so heavyweight operations are distributed. Plus, we also ensure that we don't have an entire slot idle in resources because we only have lightweight tasks in there. Better than saying that Flink is very efficient is to actually show some numbers. I can share with you some performance results from a very similar use case to the one proposed in this presentation, where we have compared Flink to Kafka Streams. Kafka Streams is a library for building streaming applications, which was also a possibility to help us solve our enrichment problem. With less computing power, in specific scenarios, Flink was able to provide us latencies almost 10 times smaller than Kafka Streams. Let me just be clear that I don't want to bash Kafka Streams at all. It's still a pretty good technology for some situations, and it even has some pros over Flink. But as I told you many times, latency is a concern for us, and that was a major point in favor of Flink. Just some other stats that I think is still interesting to show. With a setup of 16 cores from a modest CPU type, we were able to process more than 50K messages per second without noticing a considerable increase in latencies, which was something that surprised us in a positive way. Of course, not everything was perfect. There are no perfect solutions. First point I can mention is that configuring your Flink application requires some knowledge of how Flink works and about all the existing properties, which can be quite overwhelming. A second point is that preparing a setup to accumulate a Flink application was a journey by itself. We tried Amazon Kinesis and Elastic MapReduce, but none of them suited our needs for different reasons. We ended up using a platform called Ververica, which simplified the creation and management of deployments. It has a community version, which is good. And so far, I recommend it to anyone starting with Flink. And of course, there is always room for future improvements. We still have a problem to solve, which are zero downtime deployments. We have optimized the deployment process to reduce the downtime, but it's still not how we want it. To conclude, there are 3 aspects I want you to retain from this presentation. The first one is that Flink provides simple APIs, and I personally consider it to be programmer-friendly. If you have any experience with streaming, you will find no major difficulties with the data stream API. It will look very familiar. I would say it's easy to engage with Flink syntax. We can also say that it is good for streaming use cases where we need to delete state. Minus state brings many advantages. And the last one is we found that performance was amazing, at least in our experience so far. We were able to achieve high throughput and low latency without major computing resources. And we know that we can easily scale our applications, which is extremely important for us, considering our business is constantly expanding and we have to handle more and more bets every day. I will let you hear some references for the Flink and Ververica documentation. Also a pointer for a repository with a Flink implementation of our football bet enricher, where I have introduced some challenges, including a small issue. And I want to encourage you guys, even if you don't have any experience with Flink, to run it locally and submit a merge request of it. That's everything from my side. Thank you for your time. If you have any questions, you can add them in the comment box, or if you prefer, you can reach out to me directly through either LinkedIn or Twitter.
Thank you, José. José will now be answering your questions in the comment section of this stream, as he mentioned. We'll allow for a couple of minutes for both António and José to interact with you in the comment section, and then we'll close this session. Thank you for joining us for the first day of Blip's first Open Tech Week. Feel free to browse our website for more information on Blip and the Flutter group, and reach out to our speakers or to us directly here on LinkedIn if you feel the comments section doesn't cover it. I'll see you again tomorrow at 6 p.m. here on LinkedIn for our last couple of talks on this event. On our last day, we'll demonstrate how, when you really understand your technology inner works, you can make the most of it. Obrigada e até amanhã.